It's my great privilege this morning to welcome back Barbara Drossel, who has spoken for us a number of times in the Faraday Institute, both research seminar some years ago now, and also various Faraday courses. So we're delighted to see Barbara back with us again. You have the biographical details, so I won't read that all out, but simply to say that Barbara is Professor of Theoretical Physics at Darmstadt University of Technology, and in Germany, of course, and she's been particularly involved in biological systems and working on complex systems and so forth, which I'm sure she'll tell us about. I remember coming across Barbara, in fact, by reading one of her papers, a review paper, and I didn't know who Barbara was at all at that time, and was surprised to see a verse from the Bible at the top of this review on complex systems, and that gave me a hint. Oh, perhaps there's somebody interested in religion. And indeed, Barbara is also quite involved in writing and lecturing on the area of science religion over in Germany as well. And so that's another of her main activities. So today, Barbara's going to speak to us on laws of physics and God's action. Thank you very much, Barbara. Which one should you use?
Can I take this one?
You got that one? I'll show you off then.
Thank you, Dennis, for the kind introduction. Thank you, the Faraday staff, to invite me again. I'm happy to be here. It's always a joy to be here and discuss with people. The laws of physics and God's action. You know, many physicists think that their science is the most basic science, and that ultimately everything can be reduced to physics. And indeed, physics is applied to a variety of different phenomena, to regular deterministic phenomena, as well as to chaotic turbulent phenomena. And this poses two questions that are relevant to our summer course. Do the laws of physics really determine everything that happens? And then how do physics and God's action in the world fit together? If physics already prescribes what happens, is there any room for a personal God who can answer prayers? This is the outline of my talk. First, I will talk about the properties of physical laws, and I will use the example of classical mechanics, Newton's laws. And the reason is they are already 300 years old, so they have had a long history, and we can learn a lot from this history. In particular, these laws were used to build a worldview on them, the mechanistic worldview we heard about yesterday. And if you have a worldview, usually this also shapes your ideas about how God could interact with the world. And then this worldview broke down with the progress of science. But this did not cure physicists from building worldviews on their latest theories, so I will talk about this a little. And then finally, so if physics laws are not a good basis for worldviews, how should we properly view the nature of physical laws? This will be the last part of my talk, and you will see how this fits together with belief in a personal God. Let's start with Newton's laws. He suggested them in the year 1686. Philosophiae Naturalis Principia Mathematica. That was the title of this work, so mathematical principles of natural philosophy. And he suggested three very simple laws that could describe a large variety of phenomena. That was incredibly impressive. And I'm sure all of you learned them at some point in your life, but here's a quick review. So the first law is the law of inertia. It's originally due to Galileo Galilei. And it says that if there is no force acting on an object, it just keeps moving with the velocity it has. And so the reason why people earlier believed that everything comes to a rest is that's what they observed. But they didn't realize that there's always a frictional force reducing the velocity. So you can make a nice little experiment in the lecture hall. So you have some kind of support, a rail, and a glider sitting on it. And it cannot glide usually, or it quickly comes to a rest. But then you blow air between the support and the glider. And then glider just keeps on gliding very, very far. So when you reduce the frictional force, you see really the action of the law of inertia. The second law tells you how the velocity changes when there is a force. It's a famous law, F equals m times a. Force is mass times acceleration. So here you have a car of a mass of 1,000 kilogram. You want to increase the velocity by 5 centimeters per second in 1 second. And this tells you, this equation, you need a force of 50 Newton. Third law is taught in Germany in the Latin version. Actio equals reactio, action equals reaction. So to each force, there's an opposite force of equal size. So if this skater pushes her with some force, he experiences the same force and also slides backwards. Newton did more. He specified a very important force, which is the gravitational force. And you know, there's this legend of Newton sitting under an apple tree, seeing an apple falling down and realizing it's not just the earth that attracts the apple, it's also the apple that attracts the earth. So he suggested that gravitational force obeys this law, there's a universal constant, and the product of the masses of the two bodies and the inverse square distance of the centers of the two masses. And Newton's laws were incredibly successful because they could explain so much. For instance, they could unify areas of knowledge that were completely separated until then, namely Kepler's laws of planetary motion and Galileo's laws about falling bodies. So here are Kepler's laws of planetary motion. He had the best data about the planet's positions available at his time, and he found out 3 laws, mathematical laws describing the orbits of the planets. This picture shows you the first 2 laws. The first one tells you that the shape of the orbit of a planet around the sun is an ellipse, and the sun is sitting in one of the focal points. The second law is a law stating something about the velocity. The velocity is faster when you are closer to the planet and slower when you're further away. So if you connect the planet to the sun by a line and you measure the size of the area covered by this line, let's say in 1 week, and the size of this area is always the same. So for modern physicists, it's the conservation of angular momentum. That's the reason for this. And the third law is a relation between the size of the orbit, so the length of this axis, and the time it takes to go around the sun. And let me say one more thing. So all these 3 laws can be derived from Newton's law of gravitation. And I like to do it in the classical mechanics theoretical physics lecture. Here are Galileo's laws of fall. So again, there's a legend that he made experiments from the Tower of Pisa, just dropping objects and measuring the time it takes them to fall down, independent of the height from which you drop them. And then you get this law that height is related to the time by the square of the time and some factors. And also this can be derived from Newton's law of gravitation. And many more things can be derived from Newton's laws, and they're applied even nowadays when you launch a rocket, or when you build a roller coaster and want to avoid that the train jumps from the rails and the curves. So you need Newton's laws in our everyday life. So you can ask yourself, what is it that makes a scientific theory successful? And philosophers of science have reflected upon this. And here's a list of criteria suggested by Thomas Kuhn. So he's the person who coined the term paradigm shift. The good theories are accurate. This means you can do quantitative calculations. You can predict something. They must be consistent with other things that you have accepted as being correct, like Kepler's laws and Galileo's laws. A good law has a broad scope, so it can be applied to many things and not just to one particular type of event. A good law is simple and not a weird one-page long formula. This just doesn't feel right and proper. The good law is fruitful, so it inspires a lot of research. And Newton's laws have inspired a lot of research during the next 2 centuries. In particular, people have sought for the recipe to write down the trajectory of an object, just giving the forces acting on it. And those of you who have studied physics have learned Lagrangian mechanics, Hamiltonian mechanics, Hamilton-Jacobi relations. All these are just different versions of Newton's laws, trying to find the universal solution of equations. I told you that a worldview was based on Newtonian mechanics. How did this happen? First, we have to realize what are the properties of Newton's equations. Here are four important properties. Newton's equations assume there is an absolute space and absolute time. This means you can assign to every object a position that everybody can agree upon. So you can just put a universal coordinate system through space, and then everybody can agree on the position of an object. And everybody can agree on the time of an event if you can synchronize all clocks in all of the universe. The third property of Newton's equations is they are deterministic. And that's very important for the following. This means that given the positions and the velocities of all objects, given the forces interacting between them, acting between them and on them, then Newton's equations fully determine how all the objects will move. And lastly, Newton's equations are invariant under time reversal. This means when you reverse the direction of time, equations are the same. This means when you see an orbit like this one, you cannot tell which way the planet is going around. It just looks equally correct. How do you go from properties of equations to a worldview? There are a couple of steps. First, at that time it was believed that the laws were directly obtained from nature. They were directly read off from nature. And already you've heard yesterday from Alistair McGrath that things are much more complicated how you write in theory. Then the properties of the laws, the properties of equations were taken to be properties of nature. Equations are deterministic, that's true, but people concluded that nature itself is deterministic. And the laws were generalized to apply to all of nature. And now Newton's laws were deducted from a couple of observations and measurements, and it was concluded it applies to all of the universe. And then, if you make these three steps, then you end up with a mechanistic, deterministic worldview. But the world is like a big machine that is set up at some point, and then it runs exactly the way it was built and it was programmed to run, deterministically. So what happens if you try to include God in that worldview? When you make a wider worldview, in Germany we say Weltanschauung. So it's a view of everything there is. A very widespread worldview at that time was deism. God as the clockmaker who set up this wonderful clock, which is called universe, and since then it runs, or God keeps it running, he sustains it, and it runs according to the laws that God established in the beginning. So this means that there's not much room for God's additional action. Everything is already set up and happens exactly the way he programmed it. But it's not the personal God of theists, of Christianity and Judaism and Islam. But that's not the only logical option. From deism, the step to atheism is not that large. You just abolish God as the one who sustains the laws, and you say the laws themselves are the ultimate reality and that keeps the universe running. And you have to abolish the beginning. So the universe must have been running forever. Then you have an atheistic, materialistic, mechanistic worldview. And you know, this is the reason why so many scientists at first objected to the Big Bang, because they have this presupposition. But there are also logical ways to reconcile a theistic belief with the mechanistic worldview. There are two options, in fact. One is interventionalism. So just assume that God acts like an additional force. So he applies additional forces and changes the movement of the objects. And in fact, this is the view of C.S. Lewis that he exposes in the book Miracles. I was surprised to see this, but he wrote this book in the 1930s, and quantum mechanics had not yet really become established and managed by everybody. So read the book, if you know it, read it again and pay attention to this. It's really an interventionalistic view. But he defends it brilliantly. There are also ways of holding theism in a non-interventionist way and reconcile it with mechanistic view of the world. Then you have to assume God being omniscient and knowing everything beforehand, being outside time, he can just set up the initial conditions such that he already plans everything that will happen in response to what people decide and do. And I realized that in fact I was somehow raised with this view. And maybe some of you too. But remember, all these four views are based on a mechanistic view of science. And we'll come back to these four views later on, because they reappear in modern physics. So did you have to accept the mechanistic view even at that time, before the year 900? So Pierre Duhem is a philosopher of physics, or was one, and he also was a physicist. And he reflected on the different laws known at that time, and he said something really remarkable. If you compare Kepler's laws and Newton's laws, you realize they cannot both be completely exact. Because if Newton's laws are fully exact, Kepler's laws are only an approximation to reality. And if you look at how you derive Kepler's laws from Newton's laws, then you see you make two approximations. One is the mass of the sun is infinitely much larger than the mass of the planet. Otherwise, the sun moves also, and the orbit of the planet is not an ellipse. Only the difference, so the distance between the two is an ellipse. And the second assumption is there are no other planets around to disturb the orbit of the planet you consider. So you have to rule out the influence of Jupiter and everybody else. So Kepler's laws are not exact if you believe Newton's laws are exact, and vice versa. So Duhem concluded that if Kepler's laws proved to be not exact but only an idealization that works very well, we have no reasons to believe that Newton's laws are completely exact. They are also only an idealization and approximation. And you know what is strange? Pierre Duhem rejected the theory of relativity when it came. So he didn't listen to his own sermons. So how did it happen that the four assumptions that were the basis of the mechanistic worldview collapsed by the progress of science? First, there came the theory of relativity. And this was the end of absolute space and absolute time. It's not perceived in everyday life, but assumed that trains could go at half the velocity of light. Then you would observe the following. So you measure the length of the train when it's standing in the station. You find some length. Then you stand beside the rails when the train passes by at half velocity of light. You are standing here, let's say, and a friend of yours is standing here, and you mark the position where the front of the train is, at the same time where your friend marks the position where the back of the train is. And then you measure the distance between the two marks, and you find out the train is shorter. That's crazy. There's no absolute space. And then, what's even more crazy, somebody sitting in the train and observing what you are doing tells you, oh, what are you doing? You didn't measure simultaneously. The person here did measure first, and then the person back here measured. Of course you measure a shorter distance. So you don't agree on the simultaneously of putting these marks on the ground. So this is the end of absolute space and time. The end of determinism is due to chaos theory and to quantum mechanics. I told you that people try to find the recipe for writing down the solutions of Newton's equations. So writing down a mathematical function for the whole trajectory of an object. And already around 1900, Poincaré found out that this cannot be done. It can only be done for special systems that are integrable. So Poincaré tried to solve the three-body problem. So you have gravitation between three bodies. Let's take the Earth, the Moon, and some meteorite entering the space around Earth and Moon. So what you find is a very crazy trajectory that looks very chaotic and unpredictable. And eventually the meteorite gets ejected again and goes away. And if you had a slightly different initial condition, slightly different initial position, then the trajectory would quickly diverge from the one you see here in the picture. And this means in order to predict the motion of the object, you need to know the initial position and velocity with infinite precision. If you have only finite precision, you cannot forecast the evolution of the system beyond some time horizon. In practice, you can never have infinite precision. So this is the end of determinism, at least in scientific practice. And you know, quantum mechanics told us that there is even no infinite precision in theory, because Heisenberg's uncertainty principle says that precision and velocity of an object are not defined simultaneously with infinite precision. So this means the initial state is not defined sharply enough as to contain all future development. So there's an openness of the future. The present state just does not contain what happens in the future. There's some chance, some randomness, and all of you know about randomness in quantum mechanics, for instance, in radioactive decay. Let's take this radon atom. It does an alpha decay, so it emits a helium nucleus, and what is left is this radium, this is radon. So if you have lots of atoms, you can say after which time half of them are left and half of them have decayed. But nothing distinguishes an atom that decays earlier from an atom that decays later. And there are many good reasons to believe that even the atom itself does not know. So there's nothing in the atom that determines when it will decay. The invariance under time reversal is in contradiction with a clear direction of time that we observe, for instance, in the evolution of the universe. The universe started with a Big Bang and is expanding, and many irreversible transformations are happening in the universe. Years after the publication of Newton's Principia, there was a celebration at the Royal Society, and the person who was holding the chair of Newton was the same Sir James Lightfoot. He was the predecessor of Stephen Hawking. And he was a chaos theorist. He worked on turbulence, and he gave a speech on the history of classical mechanics, of chaos theory, and read what he said at the end. We are all deeply conscious today that the enthusiasm of our forebears for the marvelous achievements of Newtonian mechanics led them to make generalizations in this area of predictability, which we now recognize were false. We collectively wish to apologize for having misled the general educated public by spreading ideas that after 1960 were to be proved incorrect. And he mentions the year 1960 because starting from 1960, computers were built, and you could just simulate on the computer mechanical systems. You could just see that the majority of them are chaotic and unpredictable. So the basis for the mechanistic worldview has crashed. So what can we learn from this history? Physical laws are extremely successful, and they're even today extremely successful. Some people say Newtonian mechanics is false. I think that's not the correct view. They are still a very, very good approximation to our everyday phenomena, and we use them in our everyday life. But they are not exact. They are not an exact reflection of reality. They are idealizations. And this means they have a limited range of applicability. When you go, for instance, to very short distances where you see quantum effects, then Newtonian laws are bad. And I like this quotation by Nancy Cartwright. She was already quoted yesterday. Nature may well be underdetermined by the laws of physics. So if each law is an idealization, not exactly correct, if each law has a limited range of applicability, and there's no reason why physics should completely, fully grasp everything that happens in nature. And in any case, worldviews suggested by physical laws, that's my fifth point here, are not trustworthy And of course, they are a step beyond the limits of physics. So did this cure physicists from establishing worldviews? No. So let's take two of our modern scientific theories. One is quantum field theory. So quantum mechanics was extremely successful, and of course it became the basis of new worldviews. So quantum field theory describes elementary particles and their interactions. And you know there are essentially four fundamental types of forces or interactions, namely electromagnetic force, the weak force, which is responsible for some atomic decays. And in fact, Stephen Weinberg got the Nobel Prize for his contribution to unifying electromagnetic theory and weak interaction theory. And then there's the strong nuclear force, and there's the gravitational force. And it's a dream of many particle physicists to unify not just the electromagnetic and the weak force, but also the strong force, and there are good theories for this, and to include gravitation in it. Quantum gravity is the keyword. And they believe once you have this final comprehensive theory that describes the most basic particles that make up all the stuff in the universe and their interactions, again, you have a worldview, a theory that describes everything that happens in nature. And that's called a reductionist worldview. So particles and their interactions determine everything in nature. And this is very widespread. And I think I also believed it when I was a student, and I did a lot of particle physics. And I think many of us are influenced unconsciously by this view, which is propagated in many ways. And in different ways than classical mechanics, but still with the same conclusions. It's a view where nature of the world of physics is causally closed. So everything that happens is caused by physics, ultimately on the basis. And Stephen Weinberg himself built a wider worldview on his physics. He is an atheist, and I think yesterday we already had this quote, that the more the universe seems comprehensible, the more it seems meaningless. And we have already seen you cannot just build an atheistic worldview on some complete physical theory. You could also build a deistic worldview, so particles determining everything. Again, this sounds like deism. You know, I have the impression that many theologians, at least in Germany, have some version of a deistic worldview, because they assume God cannot interact in the world, or he doesn't really influence the world, maybe apart from human minds, because that's what possibly cannot be reduced to particles and their interactions. Interventionalism is also still alive. So just in the last 12 months, I had discussions, I think, with 2 or 3 different people holding interventionist views. This means, again, they had either a reductionist or a mechanistic view of science or physics. There are other scientists who don't accept a reductionist view. And these are in particular complexity scientists. But of course, they also suggest worldviews. So one example is Stuart Kauffman. He is a mathematical biologist, and he did a lot of work on complexity science, on evolution. He's extremely creative. So he suggested many models and theories for evolution and self-organization. And he says, and he gives many, many good reasons against reductionism, so that's a good reason to read him. And he says, you know, the world is creative. It brings forth really new phenomena, new things. So you cannot include everything just in 4 basic forces. And he says there is a spiritual dimension to the world, because life has spiritual aspects to it. And he wrote a book, the recent book is called Reinventing the Sacred. So he says, okay, the times where we believe in God are gone, but still we have this religious sense, we have the sense of awe and wonder at looking at nature. And that's what he suggests to be the new religion, just the wonder at nature, how creative it is, how many potentialities it has. And some people call this view spiritual naturalism. So it's again a closed scientific view that nature, by its intrinsic capabilities, brings forth everything. It runs by itself, even though it now has a spiritual dimension. Really new things happen. So this is less physicalist than the previous worldview, and maybe it's less well scientifically founded, because it's hard to grasp all these notions of creativity and spirituality. Again, it seems to me that theologians or Christians have, or other people have taken up this scientific view of the world and made a theology out of this. Pantheism, I think, is very close to the heart of the views of Stuart Kaufman. Or panentheism. It's also nature running by its intrinsic forces, including its spiritual capacities, its potential for evolving and creating new things. And if I understand it correctly, process theology is also born out of this scientific worldview. But some of you probably know more about it than I do. Okay, from the way how I presented things, you already could understand that I'm against basing worldviews on laws of physics. Because it always is a step beyond the laws of physics, and it takes them, or it makes them to be more than they really are. So what would be a proper view of the laws of physics? And there we have to do some philosophy of physics. And we had already part of this yesterday. So first point, and that's what we can say about any physical law, and about any natural law. They cannot be deduced by logic, just by sitting down and figuring out what the world might be like. You have to go to nature and make experiments. And that's called, they are contingent. So they could, in principle, be otherwise. You could think about a universe that works up in a different way. And there's a long tradition of relating this contingency of nature, of the laws of nature, to the will of God. So that's a nice philosophical explanation of why the laws are contingent. They are the result of a decision, and decisions are contingent. Second property, physical laws are more than mere regularities. So among philosophers of science, there's this discussion between necessitarians and regularists. So regularists hold that laws are just the observation that you have regularities. But there are good arguments against it. Necessitarians say, no, laws are something deeper. They somehow force nature to behave in this way. And the reason why they are deeper is they have explanatory power. You remember Newton's law of gravitation explaining Kepler's laws and Galileo's laws. And they radically change your expectation of what you will observe. So when Kepler derived his laws, at first he had only the data of the planet of Mars. So Tycho Brahe just didn't want to give him more data. So he had only the data of the planet of Mars, and he derived the first two laws from the data of Mars. And when he saw that the orbit of the planet of Mars is an ellipse, so he had one sample, he immediately concluded the orbit of all planets is an ellipse. You can do this conclusion only when you believe there is a law. So if it was just a regularity, maybe after seeing that 3 or 4 planets have an orbit that is an ellipse, you might conclude that the 5th planet also has an ellipse. But concluding from one sample to the general case, that means, you have grasped something deeper. And we already had this yesterday, so this, I think, so a good explanation of why there are laws that are deeper than just regularities is there is a law giver. And it's really interesting to read the discussions of philosophers of science. They somehow, they want to find out why are there laws and how do they work, and they always rule out the possibility that there is God, but they just say, we don't know our answer, we have no explanation. Physical laws do not determine everything. At least we have no reason to assume they do determine everything. It would be an extremely strong assumption to claim this. And our mathematicians have gone through this experience of incompleteness theorems. I think physics is It just needs something like this to really realize that now theory can be fully comprehensive and complete. And I told you that chaos theory and quantum mechanics essentially caused an end of determinism in classical mechanics. So to me this means physical laws just do not determine everything. The future evolution of the universe is not determined by the present state plus the laws of physics. And some people call this a causal openness of the world. So Popper wrote a nice little book called The Open Universe, which I read with a lot of pleasure a couple of years ago. John Polkinghorne holds this view. And I think that's very convincing. And for me, the best proof or example of causal openness is our brain. You know, when we think, there happens a lot in our brain that is physics and chemistry, so neurotransmitters and firing of neurons. At the same time, when we think, hopefully, we are influenced by the laws of logic. So there's something spiritual, something very abstract, having a causal influence. And this can only happen if the physical world is causally open to such other types of influences. And many people view similarly the interaction of God in the world. So there's a causal openness. And finally, physics laws are no guarantee for the future. Maybe you heard about the problem of induction. So when something happens regularly in the same way, do you have any reason to be sure that this will happen again? So can you be completely sure that the sun will rise tomorrow?
Yes, I'm sure.
And or if you have observed planets, gravitational force working at many places in the universe, how can you be sure that it's everywhere in the case? So it's always a logical jump, it's an inductive conclusion, it's not deductive. But it works very well. But still it's no guarantee. And Bertrand Russell told the story of a chicken growing up on a farm. And this chicken also observed a law. Namely, the law is every morning, every evening I get food from the farmer. And this is correct for many weeks and months. But unfortunately, one day the farmer comes and slaughters the chicken. So this small worldview of the chicken was too small. So the chicken did not see that it was part of a much bigger picture that he did not realize. And you know, often we conclude that the world will go on ever as we project it from the laws of physics. So it will go on for billions of years. But I would say we cannot be completely sure. Maybe this is just a small part of a bigger picture that we don't yet see and of deeper laws. And that, you know, relates to Christian eschatology. So I'm not a theologian, I will leave it with this, but I think this gives you a lot of food for thought. So physics alone cannot tell you for sure how the universe will evolve in the future. It cannot rule out God's interaction with the world. It cannot rule out eschatological ideas. I'm already finished.
Thank you, Barbara. There's a perception around that. Is this working or not?
Yes.
Okay, otherwise I'll come to the front. There's a perception around that physicists can explain everything, and as you said, they can't. But what about the fact that 96% of the world is either dark energy or dark matter? How do you view that as a physicist? Because what you've been talking about is a very limited understanding of only about 4% of the universe anyway. So how does that fit into your theistic worldview?
Oh, not directly, but indirectly. This is also an indication that we have not yet arrived at the end of physics. And in my view, but it's just my personal view, this issue of, in particular of dark energy, is related to this open puzzle that was mentioned yesterday. What is the nature of time and of the now? And you know, in quantum mechanics, we have not even solved the most fundamental problem of how to reconcile the measurement process with Schrödinger's equation. So, as long as we don't understand these very fundamental issues, I think we have not grasped something very fundamental about the nature of space-time. This is related to dark energy and probably also to dark matter. Maybe. I don't know.
Okay, question here, please. Yes.
Following the discussion we just had now, Roger Penrose has written a book named Cycles of Time. So far we had the idea the time is linear, and he has brought the issue that maybe time is circular. And how do we reconcile with time as linear and time as circular with the present worldview?
I mean, that's again a step beyond the boundaries of physics. What we perceive is linear time. And I mean, it's just my personal conclusion, but it's a step beyond what we can strictly conclude from physics. But I would say the expansion of the universe also is a one-way process. Of course, people believe maybe the universe collapses again and there will be a next phase, but other people think that the direction of time and the lapse of time is directly related to the expansion of the universe. So different views around, and I think it's not okay if I now just tell you one view. So of course, I have my view also on this.
Yes, we'll go for Rodney here. So,
thank you, Barbara. That's a great talk. I think there's an element of caution in there too, because you haven't said, and I wonder what your reaction would be to the idea that God then causes the quantum events that are indeterminate, or the chaotic events that are unpredictable.
No, God is on a different explanatory level. I mean, God, in the Christian view, on the theistic view, God sustains everything and keeps everything running. And so, yeah, but I think God also gives freedom to nature to develop, to evolve, freedom to us to make decisions. I would say quantum events tell us there's something indeterministic about nature. So they teach us a lesson, but I would not search for God's action in the world in quantum events, or I would not search for human free will, in particular in quantum events. It's just this indication that nature is causally open and not completely deterministic.
question here.
I would like to add to the list of things which means that physics isn't complete what's called the standard theory of elementary particles, which is the basis of all modern research, contains over 20 different parameters, which are completely arbitrary, and nobody believes that there are 20 arbitrary parameters. There must be relations between them which are not yet understood, so everybody understands that the standard model of physics must be incomplete.
Maybe physics will remain incomplete forever. Maybe we can deduce several of these parameters from one more fundamental principle, but maybe we cannot. We will see.
Well, that's an amazing confession from a physicist. Biologists like that too. Yes, it's done.
Hi, thanks for a great talk. You say that worldviews can't be based on physical laws, and I'm very much inclined to agree with you, but surely they have to be consistent, and as such, with what do we do when we know that, like you say, quantum maybe makes us confident that things aren't determined, but we are still very much aware that quantum and relativity, the two great laws of physical science today, don't match up. And so we know that there's got to be change in the future. And also, just one thing on the assumption of simplicity of the physical laws of nature. I mean, we've just heard that the standard model depends on 20 odd parameters, but actually, why should the universe only depend on a few? Why should we make that assumption?
I think we should not. I mean, there are two dangers. One of, claiming too much about the laws of physics, but the other danger is to be not sufficiently impressed by them. I mean, it's completely fascinating, the simplicity, even particle physics, by simple considerations of symmetry. and dimensions and conservation laws. You can just write down the simplest equations that satisfy these criteria that you know that have to be applied, and then they work. And they make very good predictions. I mean, we had all this hype about the Higgs particle last year. It was predicted by the theory of, or it was included in the theory of electroweak interaction, and I was very confident that it would be found because the theories are really good, so they can predict a lot, but not everything.
Over here, please, by the camera, thank you.
So in quantum mechanics, the role of the observer and the act of observing seems to play an important role. How has that been incorporated into thinking about science, religion, and
It has been abused a lot. So I think a modern view is the view of decoherence. I don't go into any details, but you know, this view that the act of observing changes things is pretty strong. I mean, quantum events or quantum measurements happen when a quantum particle interacts with a macroscopic system that is at finite temperature. And this happening is independent of whether there's an observer or not. Now, when you shoot electrons at the screen and you get a black dot somewhere, this black dot will be there whether you look at it and observe it or not. And Schrödinger's cat is either dead or alive whether you look in the box or not. I think that's the view of the vast majority of physicists, and it's much more reasonable and rational, I think. But I know other people view it differently, but I think quantum theory is misused for many purposes, and many conclusions are derived from it, and I think they don't hold water.
Yes, a question over here, thank you.
On my study of quantum mechanics, I'm afraid I would like to disagree with something fundamental here, that I wouldn't accept this idea that quantum mechanics is non-deterministic, and not very easy to discuss that in a group like this, but I think that's based on the idea of you can interpret it with the sort of many worlds interpretation or some multiverse interpretation, and you can come up with a deterministic interpretation of quantum mechanics. I mean, do you accept that?
I mean, there are deterministic interpretations, it's a many worlds view, and there are not few people who hold it. So whenever a quantum event happens, the different outcomes are realized in different worlds. But this is a highly inflationary theory, idea. And the other deterministic theory is Bohm's interpretation. But you know, it seems to me that people were just so much influenced by the mechanistic worldview that they still try to hold to it. I simply see no reason to hold to it. It's a very, very strong assumption, this determinism. And it leads into lots of philosophical contradictions, I think. So it's a weaker assumption to say the world is not deterministic, and that's what is directly suggested by the experiments, if you don't do some sophisticated interpretation.
Do you want to come back on that point? Or do you want to pursue it further? We can pursue it a little bit further if you like, because it's an interesting discussion.
Well, I don't feel I'm competent enough to. I accept your point, but you're making an assumption there that the world is you're saying the multiverse is too complicated. Well, that may be just how it is. Maybe the universe is extremely complicated.
No, but you know, this multiverse interpretation of quantum mechanics is even worse than the other multiverse theory. I mean, the normal multiverse theory just tells you there is a universe there are many, many universes, each of them having different values for these constants of nature. But this many worlds theory of Everett tells you whenever a quantum event happens, and there are trillions of them every microsecond, then the universe splits into many universes, each of them realizes one of the possible outcomes. So that's unbelievable. So, you know, even when we make a decision, the universe splits into a universe where I make the decision this way, and the universe where I make it the other way. It's absolutely crazy. And, and you know what? People don't just stick still to the determinism, they also stick to the time reversal invariance. And the reason is, if you just look at Schrödinger's equation or Dirac's equation, quantum field theory, these most fundamental theories still have these two properties, which are in contradiction to many observations and to the measurement process in quantum mechanics. It's stochastic, it's not revertible in time. So, and my field is statistical physics, second law of thermodynamics. So of course I'd like to insist that this is a very basic law. So there's a fundamental irreversibility in nature. But of course people disagree on this, and it's nice to have these discussions.
Good. Question here, and then we'll go to there. Thank you. Oh, we could go there first. That's the matter, really. No, hang on to it. You've got the mic, so you might as well.
Okay, thank you. I'm trying to bring this to a question on the view on dualism at the moment, because I think if we take on board the fact that God is spirit, in other words, constituted of something else, of another, of something different, and if we are made in God's image, then I know a fast disappearing view of a soul made of spiritual stuff, as distinct from, let's say, body and mind together, which are material. That kind of dualism, I think, opens ways of explaining divine action, human creativity, morality, everything else, in a way that actually preserves all of these complexities of different physical interpretations of the world. And I'm so sorry this is not coming, I've been in a long correspondence with Peter Clark about this, and I know he's not a dualist of that kind. But I think it's something that we perhaps should not reject out of hand, because once you've said that God is spirit, you're de facto a dualist of some kind. And if you then look at the human condition and rule out a component of the self as being made of spiritual stuff and something non-material, then I think you're taking a very big leap and somehow creating more complications than taking that view might permit. Thank you.
Okay, that's again a step beyond the realm of physics. I think physics cannot forbid dualism, but you can argue based on how you understand nature whether classical dualism is still plausible. I mean, there are alternatives like dual aspect monism. I read Richard Swinburne. I think he is one of the few modern philosophers and theologians who defend dualism, and I did not find his arguments so convincing. But on the other hand, I see that there is a lot of spiritual causal influences. I mentioned the laws of logic. The laws of physics themselves are nothing material. So it's true, in the universe there are many non-material influences at work. I myself don't yet know what to make of all this. And certainly our spiritual dimension is, at least as long as we live on this earth, inseparably intertwined with our material makeup. We cannot have consciousness without having a brain, so we need a substrate. But I think I'm not yet at the point where I can take a clear position on this issue.
Okay. Just to, since Peter Clark isn't here to clarify his own position, I mean, 2 points actually. One is his book, All in the Mind, is on the book table, and it's a really good book actually, I really recommend it. The second point is just to clarify the language of dualism so we have clarity in the discussion. So I think you were inferring that there is a use of the word dualism referring to the fact that God is spirit and the universe is material, and that's a sort of dualism. Peter Clark would surely hold to that, no problem at all. So but the dual aspect monism that Barbara just mentioned would be Peter's position when it comes to the relationship between brain and mind. So that's another use of dualism. So dualism can be used somewhat confusingly in different categories, so we just have to make sure we know which category we're referring to, I think there. Yeah. So good. How are we doing? I think we're doing well. Another question over here, please.
Thank you for your talk. I'm a physicist as well, quite long-standing. One of the point I would like to discuss with you is the extent to which our ability to process data is becoming a fundamental issue in terms of the progress of physics, and whether there is some broader issue in that in itself is fundamental as us as humans in what we're calling a spiritual world. I mean, for example, in the case of string theory, which can absorb, in principle, the issues that are non-reconcilable. There could be 10 to the 100 universes of the type that we experience at the moment, with 10 to the 24 stars each. But nevertheless, to get anywhere near a solution to that, there's at least 100 variables that would have to be really tied down, and we don't seem to be anywhere near even knowing how to begin to approach some of those. And even with relatively simple things, as you might expect, with working out the difference between the mass of a proton and a neutron with quark theory, that sort of extends the world's greatest supercomputers to their limits, and it can just about be done. Now, what I'm wanting to ask you is whether you think that the ability to process data of the sort that would be necessary to make some serious progress in our broader understanding is a fundamental issue as far as humans are concerned, or that relates to spirituality in the broader sense of a God of gaps, or whether you think that there is something else that is at the basis of this understanding.
I think there are several issues relating to this. I mean, we always have limited capability to measure things and to calculate things. That's true. But I think, if there is a law somewhere, I think you should be able to find it without processing more data than you are able of processing. I mean, if things are complicated, okay, you need computers, huge computers, but I think many people think we need some new ideas. We don't need bigger machines. When you started asking this question, I thought you may be hinting at the topic of information, which is also being discussed also by some scientists. Information is the third basis of reality in addition to matter and energy, but that's not what you meant.
That wasn't the focus of the
that wasn't the focus.
Thank you.
I wonder if I could just ask a question a little bit more about biology, just so we biologists here don't feel, too left out of the discussion. But, biologists, generally speaking, we biologists don't really talk about laws very much at all, except now and again, we think, now and again things get labelled as laws, which are a little bit, it's uncertain why certain things are labelled as laws, and we have laws of Mendelian laws, as Coates' law, and various other things come up. And then biologists spend the next couple of pages showing how there are many exceptions to these laws. So the list of exceptions becomes almost longer than the law itself. But you hinted at that, interestingly, in saying, well, the laws of physics actually don't cover all eventualities, and they also have exceptions. There are always exceptions depending on the context in which you're trying to apply them. Would you personally see a very sharp distinction between the so-called laws in biology, let's take Mendelian laws as sort of, and laws in physics? Would you see a sharp distinction there, or do you think there's a sort of gradation somehow? How do you see that?
It's more like a continuum. I think Alistair yesterday mentioned the stratified view of science, because you have the different levels of complexity. My field of research is complexity science, so I don't work with elementary particles, but I'm modeling biological systems, for instance. And there you see a model. A theory is an idealization that leaves out many, many properties, but that takes on board the most basic ingredients that are necessary to explain a phenomenon. So with the models made for modeling biological systems, I think that you see very clearly they have a limited range of applicability. were made for a certain purpose, for answering certain questions. And that have worked pretty well. There you see principles at work and regularities. But as you say, it's such a rich biological world, you always find examples that work differently. Yeah.
Would you say that out of complex systems, perhaps thinking about complex biological systems, that actually those properties that emerge are another part of your list of unpredictable events, that actually you cannot predict what emergent properties might arise from a very complex system?
That's a topic of emergence that I talked about last year. I think my talk is still on the website, because it's a very different topic.
Very good.
But,
Very recommended.
Yeah, because I mean, many people hold this reductionist view that everything in principle can be reduced to the most fundamental laws of physics, but other people argue against this. So there are new laws, new entities at each level of complexity, and I certainly hold this view because you can never view the parts without also considering the whole. I mean, there would be no elementary particles with these properties of the universe. The quantum vacuum itself didn't have these symmetries and degrees of freedom. So the parts are determined by the whole somehow. And so there's a top-down causation that's, in my view, also very important and real, and not just the bottom-up way of arguing.
Thank you. Well, I think we've worked Barbara very hard indeed, and I think you should thank her very much.